Have you ever wondered about the sheer scale of reality? How many particles make up your body, this planet, or even the universe itself? If you take a deep breath, you are inhaling approximately 50 sextillion atoms, an unfathomable number, yet minuscule compared to the 7 octillion atoms forming your entire body. Expanding further, Earth is composed of 100 quintillion atoms, and the observable universe, stretching 46 billion light-years across, contains up to 100,000 quadrillion bigentillion atoms, a number so large it defies common intuition. But these numbers, despite their enormity, pale in comparison to the truly staggering magnitudes found in certain branches of mathematics. One of the largest numbers ever conceived arises not from physics, but from an abstract mathematical puzzle known as the game of trees. In this theoretical game, we begin with a single-colored seed, which can sprout into a tree with branches, each ending in its own seeds. The objective is simple: construct as many unique trees as possible while adhering to 2 fundamental rules. First, the maximum number of seeds a tree can contain is determined by its level. Tree may first have at most 1 seed, tree 2 at most 2, and so on. Second, the game ends instantly if any newly created tree replicates an existing one anywhere in the forest, no matter how distant. Even under these constraints, something remarkable happens. If only 1 seed color is allowed, the game terminates almost immediately. Tree results in failure by the second step. Tree, allowing 2 colors, lasts slightly longer, but ultimately meets the same fate. However, when we introduce 3 seed colors, something extraordinary occurs. The forest can grow for an unimaginably long time before reaching an inevitable halt. This scenario defines tree, a number so incomprehensibly vast that mathematicians know it must be finite, yet they cannot compute its value. To put its scale into perspective, consider this. If we attempted to express tree in standard notation, the resulting number would be so large that even writing down all its digits would be physically impossible. Storing this information would require more memory than the entire observable universe could hold. In fact, theoretical physicists argue that if a human mind attempted to fully comprehend tree, the sheer quantity of information would be so overwhelming that it could collapse into a black hole under its own informational density. And yet, as vast as tree is, it remains finite, a mere speck in comparison to infinity. Infinity itself defies all attempts at containment. No matter how large a number grows, there is always another beyond it and another ad infinitum. Unlike tree, which has a definite but unfathomable endpoint, infinity stretches on without reprieve, never ceasing, never yielding. This distinction is crucial as it raises profound questions about the very nature of our universe. Could space itself be infinite? If so, what does that imply for existence? If the cosmos never ends, could it contain infinite variations of reality, including endless copies of ourselves? The universe is vast beyond measure, but it may be only the beginning of something far greater. If we continue to explore, to question, and to push the boundaries of our understanding, where might we ultimately arrive? Perhaps, in the grandest of infinities, the most staggering numbers are still waiting to be discovered. Infinities within infinities. Around 530 BCE, in the coastal city of Croton in southern Italy, a secretive assembly convenes in the dim glow of oil lamps. The air hums with whispered discussions, fervent and filled with reverence. Yet these men are not gathered to worship deities. Their devotion lies elsewhere, within numbers, geometry, and the mysteries of the cosmos. At the heart of their gathering stands their enigmatic leader, Pythagoras, a man whose words carry the weight of absolute truth among his followers. The Pythagoreans, unlike other Greek philosophical sects, revered numbers not merely as tools for measurement, but as the very foundation of reality itself. They saw numerical relationships as sacred, embodying order, harmony, and the structure of the universe. Yet, for all their mathematical zeal, their doctrine had its limits that would unravel the very beliefs they held sacred. Their greatest discomfort arose from the discovery of irrational numbers, those numbers that could not be neatly expressed as the ratio of two whole numbers. The calculation of a square's diagonal, a direct consequence of the Pythagorean theorem, yielded a value that defied their cherished framework. This realization shattered their worldview. If numbers could not be contained within finite ratios, then the universe harbored untamed infinities beyond their comprehension. For the Pythagoreans, such concepts were dangerous, even heretical. Yet, the notion of infinity could not be suppressed. It continued to perplex and challenge mathematicians and philosophers alike. Among the most famous paradoxes of infinity was Zeno's paradox. Zeno, another ancient Greek thinker, proposed a dilemma that seemed to suggest motion itself was an illusion. Imagine a journey from one point to another. To reach your destination, you must first travel halfway there. Then, you must traverse half of the remaining distance, and then half again. By this logic, an infinite number of steps must be taken before the journey is complete. How, then, can motion ever truly occur? This paradox haunted Greek philosophy, leading many to relegate infinity to the realm of metaphysics rather than physical reality. Despite these early struggles, the study of infinity would experience a profound transformation in the 19th century thanks to the revolutionary work of George Cantor. Unlike his predecessors, Cantor embraced the infinite not as an unknowable void, but as a landscape to be explored and categorized. He made a groundbreaking distinction. Not all infinities are equal. Cantor demonstrated that there exists an infinite number of natural numbers, 1, 2, 3, 4, but also an infinite number of even numbers, 2, 4, 6, 8. At first glance, one might assume the set of all natural numbers must be larger than the set of even numbers, since the latter is a subset of the former. However, Cantor revealed that these two infinities are actually the same size. Each even number can be paired with a natural number, 2 with 1, 4 with 2, 6 with 3, and so on in a one-to-one correspondence. This means they are both examples of what he termed countable infinity. But Cantor didn't stop there. He showed that some infinities are larger than others. To illustrate this, he considered the power set of a given set, the set of all possible subsets. Consider 4 elements: John, Paul, George, and Ringo. The number of ways these 4 can be combined into groups is greater than the original number of elements. The same logic applies to infinite sets. The power set of an infinite set is always larger than the set itself. This leads to the concept of uncountable infinity, a category that includes real numbers. Unlike the countable infinity of whole numbers, the set of real numbers is so vast that no pairing can match them one-to-one with natural numbers. This revelation had profound implications, shaking the very foundations of mathematics. Cantor's work was initially met with resistance. The idea that infinity could be stratified and quantified seemed absurd to many. Yet, his findings paved the way for modern set theory, which underpins much of contemporary mathematics. Despite his brilliance, Cantor faced significant opposition from the mathematical establishment. His deep engagement with the infinite took a toll on his mental health, and he spent the latter years of his life in and out of sanatoriums. Today, Cantor's legacy endures. Infinity is no longer seen as a single, amorphous concept, but as a structured hierarchy, each level revealing deeper complexities. The paradoxes that once confounded the ancient Greeks have become essential components of modern mathematics. And yet, for all our advances, infinity remains as elusive and enigmatic as ever. As we contemplate the vastness of the cosmos, the nature of numbers, and the limits of human understanding, one question lingers: are we merely scratching the surface of something even greater? Perhaps, in the pursuit of the infinite, we are destined to uncover infinities within infinities, realities beyond comprehension, waiting to be explored. Is it infinite? The past, present, and future of the cosmos are entangled in an age-old question: is the universe truly infinite? For centuries, mathematicians, philosophers, and astronomers have grappled with this idea. The ancient Greeks wrestled with infinity through paradoxes. often trying to avoid any real confrontation with the concept. Later, George Cantor formalized infinities within mathematics, differentiating between countable and uncountable infinities. And yet, for all these theoretical explorations, the question remains, do infinities exist in physical reality? Unlike the Greeks, modern scientists do not have the luxury of avoiding infinity. The universe presents them with actual infinities at every turn, black holes with singularities of infinite density, the endless expansion of space, and the sheer possibility that the cosmos itself has no boundary. With powerful mathematical tools and technological advancements, astronomers today stand at the precipice of one of the most profound mysteries in existence, the nature of infinity in the physical world. To contemplate this, imagine an island isolated from the world. A young man from North Sentinel Island moves cautiously through dense undergrowth, familiar with every rock and tree. He emerges onto a beach and looks out upon the ocean, a seemingly endless stretch of blue, encompassing his entire known world. To him, the ocean is vast but finite, bounded by the limits of his canoe. But then, one day, a white ship appears on the horizon. At first a distant speck, it gradually looms larger, an alien presence intruding upon his universe. He reacts with fear, throwing rocks and sticks, driving the intruder away. Yet, had he paused to wonder, he might have asked, if my world ends at the ocean, where did this ship come from? Could there be a greater world beyond my own? This is much like humanity's contemplation of the cosmos. For centuries, we have wondered what lies beyond the observable universe. Archytas, a Greek philosopher from the 4th century BCE, imagined traveling to the very edge of the heavens, only to reach out and find something beyond. If there were no boundary, space must be infinite. If there were a boundary, what lay past it? The question seemed unanswerable. Later, in the 16th century, Giordano Bruno argued that space was boundless and filled with infinite stars and worlds, an idea that led to his execution by the Church. Even in later centuries, philosophers like Thomas Hobbes took a more pragmatic stance. If we cannot measure infinity, why speculate on its existence? Yet, speculation persists. Today's cosmologists are armed with unprecedented observational power. The Hubble and James Webb Space Telescopes reveal galaxies from deep cosmic time. We measure the universe's expansion through redshifted light, and we detect the cosmic microwave background, a remnant of the universe's infancy. But as our observational tools improve, we encounter a new kind of boundary, not a physical one, but a temporal one. Light travels at a finite speed, roughly 300 million meters per second. This means that when we gaze at distant galaxies, we are looking back in time. We can see galaxies as they were 1 billion years ago, 5 billion years ago, even 10 billion years ago. However, beyond a certain point, around 13.4 billion years ago, there are no more galaxies to observe. Not because they do not exist, but because there was a time when galaxies had not yet formed. The observable universe, then, is limited not by a physical edge, but by time itself. The farther we look, the closer we approach the universe's beginning. Yet, paradoxically, the edge of our observable universe does not appear as an edge at all. Due to the expansion of space, those first galaxies, whose light has taken 13.8 billion years to reach us, are now an astonishing 46 billion light years away. The universe has been expanding all this time, stretching the fabric of space itself. This means that the observable universe is a sphere with a radius of approximately 46 billion light years, yet it does not imply that the universe as a whole is finite. So, is the universe infinite? The answer remains elusive. There are 3 possible scenarios for the universe's shape. It could be closed like a sphere, finite but unbounded. It could be open like a saddle, stretching out infinitely. Or it could be flat, extending endlessly in all directions. Observational data strongly suggest that the universe is geometrically flat, which implies an infinite cosmos. However, this conclusion is based on what we can observe, our local region of space. If the universe is curved on a scale beyond what we can see, it might still be finite, just vastly larger than our observable portion. Cosmic inflation theory, which describes a rapid expansion of space in the early universe, adds another layer of complexity. Inflation suggests that our observable universe is just a tiny pocket within a much larger multiverse. If inflation occurred infinitely, there may be an infinite number of observable universes, each with their own properties, constants, and physical laws. This idea shifts the question. Rather than asking if our universe is infinite, we may need to ask if the multiverse is infinite. As we probe these mysteries, our understanding remains incomplete. Just as the Sentinelese man perceived his island as the entire world, we may be bound by our own observational limits. Beyond the cosmic horizon, the universe, or the multiverse, may stretch infinitely, or it may loop back upon itself in ways we cannot yet perceive. The question of infinity is not just a scientific challenge, it is a philosophical one. If the universe is infinite, does that mean every possible version of reality exists somewhere? Are there infinite copies of you, reading these words in infinite variations of this very moment? These ideas, as unsettling as they may be, are the natural consequence of contemplating an unbounded cosmos. Like those before us, we are left to wonder. But unlike those before us, we have tools, mathematics, and observations to push the boundaries of our knowledge further. Whether the universe is infinite or not, our pursuit of understanding is itself boundless. And perhaps, in our relentless search for the infinite, we are touching upon something even greater than infinity itself, the infinite capacity of human curiosity. The cosmos stretches out before us in all directions, an unthinkably vast expanse of galaxies, stars, and cosmic dust. Yet, despite its grandeur, there is nothing in the observed structure of the universe that suggests an edge or an invisible barrier hemming in the galaxies we see. Though it is improbable that the universe began in a state of perfect equilibrium, the large-scale homogeneity of space suggests an almost uniform distribution of matter and energy. Space appears to be expanding uniformly everywhere, reinforcing the notion that the universe has no center. On scales larger than 230 million light-years, the observable universe maintains a remarkable consistency. No regions appear significantly hotter or denser than others. Scientists have confirmed this through the cosmic microwave background radiation and afterglow from the universe's infancy, just 300,000 years after the Big Bang. This baby picture of the cosmos reveals only the faintest variations, differences of just a few parts in 100,000. This remarkable uniformity is one of the strongest pieces of evidence supporting the theory of cosmic inflation. Inflation proposes that, in the first fraction of a second after the Big Bang, the universe underwent an exponential expansion, doubling in size approximately 80 times. This would have ironed out irregularities, leaving behind the smooth, homogeneous structure we see today. Yet, if inflation occurred as theorized, it implies that the universe extends far beyond what we can observe, perhaps to an extent that is, for all practical purposes, infinite. Thomas Hobbes once argued that speculating about an infinite universe was futile, since we cannot measure or test its existence. There is no reason to concern ourselves with what lies beyond our cosmic horizon. Even with modern technology, we remain bound by the speed of light, unable to access regions of the cosmos beyond our observable limit. But while our ability to directly probe the unknown is constrained, our imagination is boundless, and speculation, however unfounded, has always been an essential part of scientific discovery. Imagine a Sentinelese tribesman setting out in his canoe across the ocean. From his perspective, the ocean seems boundless. He could sail for years without reaching an edge. But in reality, if he were to navigate far enough, he would find himself back where he started. The Earth's surface is finite, yet without boundaries, because it is curved. Cosmologists propose that space may behave similarly, though three-dimensional instead of two. If the universe possesses positive curvature, like a sphere, Traveling in any direction indefinitely would eventually bring an observer back to their starting point. If it is negatively curved, like a saddle, parallel lines would diverge infinitely. If it is flat, those lines will remain parallel forever. The nature of this curvature determines whether the universe is ultimately finite or infinite. In the 1930s, Edwin Hubble attempted to infer the universe's shape by counting galaxies along a given sight line, observing how their density changed with distance. The idea was straightforward. In a curved universe, the number of galaxies should increase or decrease at certain rates, depending on the type of curvature present. However, the universe is not static. Galaxies evolve over time, complicating direct measurements. More sophisticated techniques were needed. With the explosion of cosmological data in recent decades, astronomers have devised new methods to probe the geometry of the cosmos. One such technique involves standard candles, highly luminous supernovae whose intrinsic brightness is well understood. By measuring how their light dims with distance, we can estimate the shape of space. Another method involves standard rulers, patterns imprinted in the cosmic microwave background by early universe sound waves. These methods, combined with high-precision instruments like the Wilkinson Microwave Anisotropy Probe, have enabled astronomers to measure the total mass-energy content of the universe. Crucially, these measurements have revealed an unsettling result. Despite extensive efforts to detect cosmic curvature, the universe appears to be flat, at least within the limits of our observational precision. If the universe were positively curved, light from distant galaxies would subtly bend, altering our measurements. If negatively curved, it would diverge in predictable ways. But as far as we can determine, space extends in all directions without significant deviation, resembling an infinite flat plane. So, does this mean the universe is infinite? Not necessarily. Just as the ocean appears flat from a low vantage point, but is curved on a planetary scale, the universe may also possess curvature beyond what we can observe. Current instruments can measure cosmic curvature to a precision of 1 part in 400, an extraordinary level of accuracy, yet not absolute. If curvature exists, our inability to detect it means that the universe must be at least 37 trillion light-years in diameter. This lower bound dwarfs our observable bubble, which spans a mere 92 billion light-years. And yet, even this lower bound does not preclude the possibility of infinity. The true extent of a universe could be far greater, potentially beyond all conceivable measurement. If the universe is infinite, it would contain an infinite number of galaxies, planets, and perhaps even identical copies of ourselves, existing somewhere out in the vastness of space. Ultimately, the question remains unresolved. Science may never be able to confirm whether the cosmos is truly infinite or merely staggeringly large beyond our observational reach. But even in our bounded view of the universe, the vastness we can see already stretches the limits of human comprehension. If there is more beyond, we may never know for certain, but the pursuit of that knowledge continues, driven by the same curiosity that led us to ask these questions in the first place. Living in an infinite universe, a scientific and philosophical inquiry. On August 15th, 1977, an event occurred that still echoes through the annals of astronomy and astrobiology. A volunteer astronomer at Ohio State University, Jerry Emin, was meticulously reviewing pages of data recorded by the Big Ear radio telescope. This was a time before the ubiquity of advanced computer processing, so the telescope signals were logged manually, with signal strength encoded numerically from 0 to 9, then continuing with letters from A to Z for stronger detections. Amid the humdrum of ordinary cosmic noise, Emin encountered something extraordinary, a sequence unlike anything previously observed, 6EQUJ5. This notation represented a distinct and powerful spike in radio noise, surpassing any signal ever detected before. Realizing the significance of what he had found, Emin hastily circled the sequence and inscribed a single word beside it. From that moment forward, this anomalous burst of radio waves has been immortalized as the WOW signal, At the time, Big Ear was engaged in an ambitious quest, part of the burgeoning field of the search for extraterrestrial intelligence. Scientists had little certainty about the characteristics of an extraterrestrial transmission, but they did know that any genuine interstellar message would likely exhibit an unmistakably structured pattern, precisely what the WOW signals seemed to be. Yet, despite decades of scrutiny, the signal remains enigmatic. It was powerful, singular, and never repeated. It seemed to originate from deep space, yet no known celestial body or astrophysical phenomenon could be definitively linked to it. Was this a cosmic accident, or could it have been our first and only detected whisper from an alien civilization? While most scientists lean towards a natural explanation, the signal's ultimate source is still unknown. However, the deeper question remains: in an infinite universe, is it truly possible that we are alone? The boundless cosmos and the certainty of extraterrestrial life. The concept of an infinite universe carries profound implications. If the cosmos extends without end, then life beyond Earth is not merely probable, it is inevitable. This does not mean that alien civilizations must exist within our observable horizon, but rather that in the vast expanse of all that is, every conceivable form of life must, by necessity, emerge somewhere. From the simplest microbial entities to civilizations capable of harnessing the energy of entire galaxies, an infinite universe ensures the reality of their existence. Yet, how do we frame this assertion within a rigorous scientific structure? Theoretical physicist Sean Carroll offers 4 fundamental possibilities regarding the nature of our universe. Finite in both space and time. Infinite in spatial extent but finite in temporal duration. Finite in space but infinite in time. Infinite in both space and time. Each scenario carries its own philosophical and scientific consequences. If the universe is both spatially and temporally finite, then the number of habitable worlds is strictly limited, and the existence of extraterrestrial life is an open question dependent on the specific probabilities governing abiogenesis. However, if the cosmos is infinite in any regard, whether in space, time, or both, then the very nature of probability dictates that life must not only exist but be replicated endlessly across the void. Infinity and the repetition of existence. Consider a universe that is infinite in spatial extent but finite in time. Within such a construct, there would be limitless regions of emptiness, but also boundless domains of structure. This duality aligns with the mathematical principles of infinity, much like how there exist both infinite even numbers and infinite counting numbers. If we accept that the cosmos contains unending permutations of matter, then the inescapable conclusion is that there are infinite occurrences of planets, stars, galaxies, and even intelligent civilizations. In this framework, the very notion of uniqueness dissolves. Every arrangement of atoms that composes our world, including our own bodies and minds, would be mirrored an infinite number of times elsewhere. Somewhere in the depths of the universe, exact copies of Earth must exist, each inhabited by identical beings contemplating their own existence in the same manner that we do. More unsettlingly, there must also be slight variations, Earth-like planets where history unfolded with minor deviations, where alternate versions of ourselves live different lives, and where the WOW signal is not just a fleeting anomaly, but the beginning of an interstellar dialogue. Quantum oddities and the emergence of the unimaginable. If we extend our consideration to a universe that is temporally infinite, the implications become even more bizarre. In an infinitely old cosmos, not only would every physical event repeat an infinite number of times, but even the most improbable occurrences would become inevitable. Quantum mechanics dictates that subatomic particles continuously flicker in and out of existence due to vacuum fluctuations. While the spontaneous emergence of something as complex as a star or a planet from the void is vanishingly unlikely, given infinite time, such occurrences would eventually transpire repeatedly. This notion leads to one of the strangest thought experiments in cosmology, the Boltzmann brain paradox. Named after the 19th century physicist Ludwig Boltzmann, This concept proposes that if quantum fluctuations persist indefinitely, then not only can physical objects materialize randomly, but so too can entire conscious minds. In a universe of eternal duration, isolated human brains, complete with artificial memories, sensory experiences, and self-awareness, could emerge spontaneously from the vacuum, experiencing what appears to be a full and consistent reality before inevitably dissolving back into chaos. The unsettling corollary is that statistically, there should be far more Boltzmann brains than biological beings, suggesting that our own perception of existence may be an illusion. The final paradox: are we real? If we take these possibilities seriously, the question arises: are our thoughts, memories, and experiences genuinely tied to a coherent and structured universe, or are we ephemeral consciousnesses conjured into being by the random churn of quantum fluctuations? While such a notion seems absurd, it follows logically from the premises of an infinite and eternal universe. Yet, even within this unsettling framework, one truth remains unshaken. Whether we are biological entities living on a planet orbiting a star, or fleeting manifestations of a probabilistic cosmos, our experiences are real to us. And in an infinite universe, where every possibility must eventually be realized, the mere act of contemplating existence is itself a fundamental part of the cosmic equation. Thus, whether or not the wow signal was a genuine alien transmission, the infinite nature of the cosmos guarantees that somewhere out there such signals must exist. In an unbounded universe, life is not just a possibility, it is a certainty. And so, as we gaze into the abyss of infinity, we may take comfort in the knowledge that in some distant sector of space-time, intelligent beings are gazing back. Antonio Padilla posits that the universe may eventually reach its Poincare recurrence time, a staggering billion years into the future. This incomprehensibly long timescale marks the statistical moment when all particles within a finite system would, by sheer probability, return to their original configuration, initiating a cosmic cycle of repetition. This concept, rooted in statistical mechanics, suggests that even within a finite universe, eternity manifests through recurrence, raising profound implications for the nature of time and existence. Yet, when we extend our contemplation beyond the realm of a finite cosmos to an infinite one, we encounter an entirely different set of challenges. An infinite universe, by definition, encompasses boundless possibilities, each occurring not just once, but an infinite number of times. This leads directly to the measure problem, an issue that challenges our ability to assign meaningful probabilities to events in an unbounded cosmos. If every event, no matter how improbable, occurs infinitely often, then how do we differentiate between the likely and the unlikely? In such a framework, our classical approach to probability collapses, as no finite measure can adequately describe an infinite reality. The implications of this are profound. In attempting to extrapolate from the observable universe, an entity that is, at best, an infinitesimal fraction of the whole, we face an epistemological deadlock. The nature of infinity renders any finite fraction of it effectively zero. This realization forces us to reconsider the reliability of our empirical observations and theoretical models. If our observable cosmos constitutes precisely 0% of the totality of existence, then to what extent can our scientific conclusions hold universal validity? This dilemma extends beyond mere mathematics or physics. It strikes at the very core of cosmology. If we cannot meaningfully assign probabilities, if we cannot assert laws that extend beyond our infinitesimally small observational domain, then can we truly claim to understand the universe? Our theories of the Big Bang, the evolution of the cosmos, and even the fundamental laws of physics may be applicable only within the narrow confines of our perceptible reality. Beyond that, they may be little more than approximations, useful, but ultimately insufficient in the face of the infinite unknown. This leads to an unsettling but necessary existential confrontation. The Greeks, wary of the implications of infinity, sought to sidestep the paradoxes it introduced. More than 2 millennia later, despite the advent of transfinite mathematics and sophisticated cosmological models, we find ourselves grappling with the same fundamental conundrums. While we have refined our ability to describe aspects of infinity, we are no closer to comprehending its full nature. In many ways, infinity remains a conceptual abyss, an entity that defies human cognition, challenging the very framework by which we understand existence. But even this is merely a beginning. The infinite universe, if it indeed exists, is but one manifestation of infinity within cosmological theories. There are deeper, perhaps even more troubling infinities lurking at the edges of our understanding, those that reside within the quantum fabric of reality, within the singularities of black holes, and within the very foundations of mathematics itself. These infinities are not just abstract constructs, but are woven into the fabric of existence, shaping both the known and the unknowable. To confront them is to confront the limits of human comprehension and, perhaps, to glimpse the edges of a reality far beyond our grasp. Polish-born mathematician Benoit Mandelbrot was captivated by the apparent disorder of both the natural and human-made world. He sought to uncover underlying patterns in everything from financial market fluctuations to the rugged contours of coastlines. In 1958, his journey brought him to New York State, where he joined the IBM Research Center in Yorktown Heights, an institution dedicated to advancing both computer hardware and the mathematical theories underpinning computational technology. Over the next 35 years, Mandelbrot's focus was not on improving computers themselves, but rather on demonstrating how they could revolutionize the study of mathematics. In 1980, Mandelbrot became one of the first to use computer graphics to visualize structures that would have been nearly impossible to comprehend using traditional mathematical tools. Through relatively simple equations, he unveiled a strikingly intricate form of geometry, which he termed fractal, derived from the Latin word for broken or shattered. Fractals are characterized by self-similarity across scales. No matter how far one zooms in or out, the structure retains its complexity. Unlike conventional geometric shapes, fractals never resolve into simpler forms, revealing infinite detail at every level of magnification. Mandelbrot's computer-generated Mandelbrot set provided a vivid illustration of this phenomenon, but more significantly, he demonstrated that fractal geometry is embedded in the natural world. Self-replicating patterns appear in fern leaves, the fractal branching of Romanesque broccoli, and even in the large-scale distribution of galaxies. This led to the profound question, could the universe itself be fractal? Observations have since shown that at the largest scales within our observable universe, homogeneity dominates. However, the possibility remains that on even grander, unobservable scales, fractal-like structures could persist. This naturally ties into a larger enigma, the infinite nature of the cosmos. Our universe is expanding, akin to dough rising in an oven, with every galaxy drifting further apart. If it emerged from an initial singularity, then our observable universe represents only a finite portion of that original entity. Yet, despite its continued expansion, this measurement remains bound by the limits imposed by the speed of light, the farthest distance that light has traveled since the beginning of time. As the universe expands, its density decreases. While local structures such as galaxies remain bound by gravity, at cosmic scales, everything moves apart at an accelerating rate, measured at approximately 70 kilometers per second per megaparsec. If this trend persists indefinitely, the universe faces a so-called heat death, an ultimate fate in which all thermodynamic processes cease as entropy reaches its maximum. However, despite this relentless expansion, there is no final moment of cosmic dissolution. The observable universe will continue to grow indefinitely, eventually reaching an infinite scale. Yet paradoxically, even with infinite time, our capacity to explore this ever-expanding cosmos remains finite, as expansion perpetually outpaces our ability to reach new regions. Tracing this expansion backward in time, the cosmos contracts, growing denser and hotter until it reaches a state that defies our known physical laws. Theoretical physics suggests that at a minuscule scale, approximately 1 Planck length, or 1.6 times 10 superscript 3 meters, the universe enters a regime dominated by quantum uncertainty, where conventional notions of space and time cease to function predictably. This length, first identified by physicist Max Planck, represents a fundamental limit beyond which our understanding of physics collapses. While current models propose that the universe may have originated from an infinitely small, infinitely dense singularity, this assumption presents paradoxes. If the cosmos truly emerged from an infinitely compressed state, then its pre-Big Bang existence could, in principle, have lasted an infinite amount of time. This raises the possibility that, rather than being 13.8 billion years old, our universe could be infinitely older. Thus, through observations of cosmic expansion and contraction, we are led to a profound paradox, one where infinite largeness and infinite smallness coexist. How, then, can we reconcile these opposing infinities? The answer remains elusive, trapped within the constraints of our current understanding. Yet, as our mathematical tools evolve and our ability to probe deeper into the mysteries of space and time advances, we edge ever closer to unraveling the infinite complexities of our cosmos. It is true that the observable universe is currently expanding, yet this does not necessitate that the entire infinite cosmos follows the same trend across all of infinite time. Cosmologists have proposed that our local universe, the portion we can observe and an indeterminate expanse beyond, represents a limited region of inflation within a vast, eternal, and infinite whole. This concept, known as eternal inflation, was first introduced by Alan Guth in 1979 and later expanded upon in the early 1980s by Andre Linde, Andreas Albrecht, and Paul Steinhardt. Within this framework, our universe is merely a minuscule fragment of an eternally inflating multiverse. However, inflation does not occur uniformly across this infinite expanse. Different regions experience inflation at different times, in different locations, and to varying degrees. The logical consequence of this perspective is that our universe is but one among an infinite number of bubble universes, distinct pockets of space-time that have emerged from the underlying infinite reality. Each of these universes within the multiverse may exist at different stages of cosmological evolution, governed by physical laws that might diverge drastically from our own. Yet, they remain forever inaccessible to us, separated by the insurmountable chasm of infinite space. Exploring multiverse theories inevitably opens a Pandora's box of new infinities. To accommodate the profound complexities arising from quantum mechanics and high-energy physics, many theorists turn to N-theory, a unifying framework within string theory. This theory postulates that our observable reality emerges as a fleeting intersection of higher dimensional constructs, and that countless such intersections might exist simultaneously, flickering in and out of existence as the broader bulk of hyperspace evolves. Thus, we are compelled to consider not only an infinite number of universes within our familiar three-dimensional space, but also a multiverse comprising a limitless variety of dimensional configurations. And once again, there is no fundamental reason to assume that these parallel universes adhere to the same physical laws as our own. The strength of gravity, the masses of fundamental particles, and the very constants that govern reality could differ from one universe to another, producing an incomprehensibly vast array of possibilities. From our limited perspective, the Big Bang represents the smallest scale at which we can probe, while the ultimate heat death of the universe defines the largest. Yet, if an omnipotent observer could zoom in or out beyond our constraints, they might discover that our expanding bubble is but a single layer of complexity within an even grander structure. This notion finds echoes in Roger Penrose's conformal cyclic cosmology. According to this theory, when our universe has expanded to an infinite scale from our perspective, it may paradoxically become the seed for a new, infinitesimally small Big Bang, initiating an entirely new cycle of cosmic evolution at a different scale. However, for all their conceptual elegance, these ideas remain theoretical. As with many aspects of infinity, they present challenges that may be fundamentally insurmountable. The very nature of infinity implies that definitive empirical evidence for an infinite cosmos may be forever beyond our grasp. Thus, the scientific pursuit remains focused on searching for signs of finiteness, tracing the layers of cosmic structure as far as we can, continuing to follow the turtles, wherever they may lead.
Where are we truly located? Not just your house number, nor the name of your street. Not merely your town, city, or even your country on a continent of Earth. But where is Earth, really? It resides in the solar system, nestled between Venus and Mars. A familiar enough answer. Yet this solar system is more than just its planets. It's a dynamic hub of activity, dominated by the Sun's gravitational influence, extending outward into the enigmatic Oort cloud, a vast, spherical shell of icy objects and ancient comets marking the Sun's cosmic reach. Still, the Oort cloud is but a minor structure within the local interstellar cloud, a faint mist of gas and dust that itself swims within the local cavity, an expanse of relatively low-density space carved out by ancient supernovae. This local cavity is part of the Orion arm of the Milky Way, a galaxy defined by its magnificent, spiraling arms of stars and cosmic dust, all circling a supermassive black hole cloaked in mystery at its galactic core. The Milky Way spans more than 100,000 light-years, a staggering size on human terms, yet in the cosmic context, it is but a fragment. As we zoom outward, the local group emerges, a collection of 30 to 50 galaxies bonded together by gravity. Among them is Andromeda, a galactic titan twice the size of the Milky Way, hurtling toward us on an inevitable collision course. In a few billion years, these galaxies will collide, their stars pulled and scattered before settling into a new, merged form. But even this cosmic drama is a mere footnote at greater scales. The local group is part of the Virgo supercluster, a sprawling congregation of thousands of galaxies. Yet Virgo itself is dwarfed by the Laniakea supercluster, a monumental structure hundreds of millions of light-years across. Within Laniakea, filaments of galaxies connect like threads in a vast cosmic web, weaving through voids such as the Boötes Void, a chilling expanse 330 million light-years across that holds fewer than 60 known galaxies, a near emptiness in the fabric of existence. As we continue to zoom out, we reach the edge of the observable universe. Here, light has journeyed to us for 13.8 billion years, carrying whispers from the dawn of time. However, the universe's expansion means that the true edge lies much farther, 46 billion light-years away in every direction, forming a sphere 93 billion light-years in diameter. Beyond this boundary lies the unknown. At scales this vast, the observable universe itself becomes a map of grand structure. Galaxies cluster into groups, which in turn form superclusters and filaments. Yet even within this magnificent order, scientists encounter what they term the end of greatness, a conceptual limit to cosmic structures that defies further hierarchy. It begs the question, why is the universe so structured? How did a primordial soup of particles evolve into this stunning array of stars, galaxies, and voids? Was this order inevitable, or is it the result of some profound cosmic symmetry? Even more importantly, how do we know? Mapping the cosmos. The story begins in 1502 with Nicholas Copernicus, a young polymath meant to be studying medicine in Padua, Europe's center for healing. Yet his mind was not confined to earthly ailments. By night, he pored over the works of Aristotle, Plato, and Ptolemy, finding inconsistencies in the prevailing geocentric models of the cosmos. A decade later, in quiet defiance of convention, he drafted his revolutionary theory: Earth is not the center of the universe. We are but one planet orbiting the Sun, unexceptional in a vast cosmic dance. Copernicus delayed publishing his ideas for fear of the upheaval they would cause. It wasn't until his 70s, some say on his deathbed, that his seminal work finally emerged, shaking the foundations of science, philosophy, and religion. The Copernican principle, as it is now known, declares that Earth holds no privileged position in the cosmos. This seemingly humbling revelation opened the door to boundless exploration. If we're not special, what else might be out there? Modern cosmology rests on this principle, supported by discoveries like the cosmic microwave background radiation. This faint, primordial glow permeates the universe, no matter where you look. Discovered in the mid-20th century, the CMBR is a relic of the early universe, emitted when matter cooled enough for light to travel freely for the first time. Its uniformity, 2.7 Kelvin across all directions, suggests that, on large scales, the cosmos is homogeneous. Yet here lies a paradox. Our local cosmic neighborhood teems with structure, galaxies, clusters, and superclusters connected by filaments of matter, interspersed with vast voids of near-nothingness. How can the universe be both uniform and filled with such intricate patterns? The answer lies in the interplay of two opposing forces, expansion and gravity. Shortly after the Big Bang, the universe underwent a period of rapid inflation, stretching any initial irregularities across vast distances. As expansion slowed, gravity began to dominate, causing denser regions to pull in surrounding matter. These overdensities grew, forming stars, galaxies, and eventually the vast cosmic web we observe today. But where did these initial fluctuations come from? The first hints emerged in 1989 with NASA's Cosmic Background Explorer. COBE provided the first baby picture of the universe, mapping tiny variations, anisotropies, in the CMBR. These were incredibly subtle, 1 part in 100,000, but they marked the seeds of cosmic structure. This groundbreaking discovery inspired successive missions, each sharpening our view. The Wilkinson Microwave Anisotropy Probe in 2001 and the European Space Agency's Planck satellite in 2009 revealed increasingly fine details of these early fluctuations. Together, they confirmed that tiny quantum irregularities, stretched by inflation and sculpted by gravity, gave rise to the galaxies and clusters we see today. On Earth, telescopes like the Sloan Digital Sky Survey have taken mapping to new heights. Nestled in New Mexico, SDSS collects light from thousands of celestial objects simultaneously, using custom-drilled aluminum plates and fiber optics to measure their distances and motions. This meticulous work has revealed structures like the Laniakea supercluster, our galactic home, and the Sloan Great Wall, a billion light-year expanse of galaxies. But even these colossal structures pale in comparison to recent discoveries. In 2021, astronomers identified the giant arc, a structure spanning 3.1 billion light-years, so vast it challenges our assumptions about cosmic uniformity. At this scale, the universe appears as a vast network, filaments of matter connecting clusters, with dark voids stretching between them. This raises a surprising question. What is the nature of this cosmic web? Is it like a soup of meatballs floating in empty space? Or is it more like a honeycomb or sponge, with dense regions separated by voids? Cosmologists have debated these metaphors for decades, not for their whimsy but for their profound implications about the underlying physics of the universe. The truth, as always, lies in the data. By combining observations from ground-based telescopes, space missions, and advanced simulations, scientists are gradually revealing the grand architecture of the cosmos. It is a structure born from chaos, shaped by forces we are only beginning to understand, and filled with patterns that echo across billions of years. And as we continue to map the universe, we may yet uncover deeper truths about its nature and our place within it. As we push the boundaries of our understanding, each discovery leads to new questions. The universe, with its vast structures, appears to follow certain rules, but the full extent of its organization remains elusive. The cosmic web, a network of galaxies, clusters, and voids, suggests a pattern, but what determines its shape? Is the universe governed by simplicity or complexity? The largest structures we see today are a result of billions of years of cosmic evolution. Fluctuations in the early universe grew into galaxies and clusters, But why did those fluctuations exist in the first place? These irregularities are thought to be quantum in origin, tiny uncertainties amplified during inflation. Yet this explanation leaves room for deeper mysteries. What drove inflation? What is the true nature of dark energy, which now accelerates the universe's expansion? One tantalizing idea is that the universe's structure may reflect the geometry of spacetime itself. Einstein's theory of general relativity showed that gravity isn't merely a force but the warping of spacetime by mass and energy. On cosmic scales, this warping creates the scaffolding for the web-like structures we observe. Dark matter, though invisible, acts as the glue that binds galaxies together, while dark energy stretches spacetime apart. Together, they shape the universe into a delicate balance of connection and isolation. And yet, even this balance raises profound questions. Recent discoveries, like the giant arc and the KBC void, a proposed supervoid nearly 2 billion light-years across, challenge our assumptions about the universe's uniformity. Are these anomalies rare exceptions, or do they hint at something deeper about the fabric of reality? Mathematically, the universe's structure invites comparisons to familiar patterns, a sponge, a honeycomb, or a soup. But the true answer may be stranger than any metaphor. The interplay between cosmic forces, gravity, expansion, and the unknown drivers of dark energy and dark matter creates a complexity that defies simple explanation. This complexity is both humbling and inspiring. It reminds us that our understanding of the cosmos is still in its infancy. We have mapped only a fraction of what exists, and the tools at our disposal are improving with each passing decade. Telescopes like the upcoming James Webb Space Telescope and observatories such as the Vera Rubin Observatory promise to unlock new realms of knowledge, from the earliest galaxies to the nature of dark matter. In this grand effort to map the cosmos, we are not just charting stars and galaxies, we are seeking to understand the origins of everything, including ourselves. Every map, every image, and every spectrum collected tells a story about where we come from and where we might be headed. The structure of the universe. In the mid-20th century, as the Cold War raged, two competing schools of thought emerged on opposite sides of the Iron Curtain. In Princeton, New Jersey, a mild-mannered Canadian physicist named Jim Peebles pondered how tiny fluctuations in the early universe could grow into galaxies and clusters. His theory imagined the universe as a meatball soup, matter clumped together by gravity into roughly spherical regions, leaving vast, low-density voids. This bottom-up model suggested that small structures merged to form larger ones, eventually building the cosmic web we see today. Meanwhile, in Moscow, Yakov Zeldovich, a veteran of the Soviet atomic program, was thinking along different lines. Zeldovich envisioned the universe as a series of two-dimensional pancakes of matter. According to his top-down theory, these large-scale structures formed first, with galaxies emerging where the pancakes overlapped, creating filaments and clusters. Between these filaments lay vast voids, shaping the universe into a series of interconnected planes. The two models, meatballs versus pancakes, reflected not just scientific preferences but also the contrasting intellectual cultures of their creators. Zeldovich, constrained by Cold War politics, rarely traveled outside the USSR, so his ideas spread more slowly than Peebles'. In contrast, Peebles' theories gained traction in the West, bolstered by a growing body of observational evidence. But neither theory fully captured the universe's complexity. A new perspective emerged through an unlikely intermediary, Martin Rees, a British astronomer who acted as a bridge between the American and Soviet schools. Rees's postdoctoral researcher, Richard Gott, met Zeldovich at a 1977 conference in Estonia, where they exchanged ideas that would lead to a third, hybrid model. Inspired by both schools, Gott proposed that the universe resembles a sponge, a structure neither entirely clumpy nor flat. In this model, high-density and low-density regions are complementary, connected in a way that balances the competing forces of gravity and expansion. The sponge-like topology suggested that matter and voids were intricately linked, creating a universe that was both complex and self-similar at different scales. As telescopes improved and surveys like the Sloan Digital Sky Survey mapped the cosmos in unprecedented detail, Gott's sponge model found strong support. Observations revealed filaments of galaxies weaving through vast voids, forming a cosmic web. Neither the isolated clumps of Peebles' Meatballs nor the flat sheets of Zeldovich's pancakes fully captured this intricate network. Instead, the sponge-like structure provided a more accurate description of the universe's vast, interconnected architecture. Yet, even as these maps revealed the grandeur of the cosmic web, they also uncovered something unexpected, a phenomenon scientists call the end of greatness. Beyond scales of about 1 billion light-years, the universe appears homogeneous and isotropic, the same in all directions. The intricate structures of galaxies, clusters, and filaments give way to a smooth, uniform expanse. This transition raises profound questions. Why does structure vanish at this scale? Why does the universe become so unstructured, so featureless, beyond a certain point? The answer lies in the interplay of cosmic forces. On small and medium scales, gravity dominates, pulling matter together to form the structures we observe. But on the largest scales, the universe's expansion, driven by dark energy, becomes the defining force. The acceleration caused by dark energy stretches spacetime itself, smoothing out irregularities and erasing the clumps and filaments that define smaller scales. This shift reflects a fundamental aspect of the universe. While local regions are shaped by gravity, the cosmos as a whole is governed by the principles of relativity and thermodynamics. The universe's homogeneity at large scales aligns with the cosmological principle, which states that the universe is uniform when viewed from a sufficiently broad perspective. The end of greatness serves as a humbling reminder of the balance between order and chaos. On one hand, gravity creates intricate patterns, weaving galaxies and filaments into a grand cosmic web. On the other, dark energy works to erase these structures, pulling the universe toward an ultimate simplicity. The universe, in its sponge-like complexity and eventual uniformity, invites us to look beyond simple metaphors and toward the profound interplay of forces that shape everything we see. It is a story of contrasts, of gravity and expansion, structure and smoothness, and the ongoing quest to understand a cosmos that defies our imagination. Imagine standing on the equator in Ecuador, gazing up at the night sky with a powerful telescope. You carefully measure the temperature of the cosmic microwave background radiation, the faint afterglow of the Big Bang. Now, imagine flying to Indonesia, on the opposite side of the Earth, and making the same measurement. Astonishingly, the temperatures match to an extraordinary degree of precision, differing by no more than 1 part in 100,000. Yet these regions of the universe are now separated by tens of billions of light-years, far too distant to have ever communicated through the exchange of light or heat in the 13.8 billion years since the Big Bang. How, then, could they have arrived at such a precise agreement in temperature? This conundrum is known as the horizon problem, one of the most profound challenges in cosmology. The extreme uniformity of the CMBR, while essential to our understanding of the universe, defies the basic principles of thermodynamics. It suggests that regions of space separated by vast distances must have once been close enough to interact. The solution to this mystery lies in a radical idea, inflation, a theory first proposed by physicist Alan Guth in the 1980s. Inflation posits that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential expansion. Space itself grew so rapidly that regions once in close contact were flung apart faster than the speed of light. This does not violate the cosmic speed limit, as it is space itself, not objects within space, that expanded. Through inflation, the horizon problem vanishes. The regions you observe from Ecuador and Indonesia were once so close that their temperatures could equalize. Then inflation stretched these regions to immense distances, locking in their uniformity and creating the seemingly homogeneous universe we observe today. But inflation does more than solve the horizon problem. It explains why the universe is flat, a property confirmed through precise measurements. Flatness, in this context, refers not to a lack of dimensions but to the universe's geometry. In a flat universe, parallel lines never converge, and the angles of a triangle always add up to 180 degrees. Observations of the universe's density, coupled with measurements of the CMBR, strongly support this flat geometry, a hallmark prediction of inflation. Inflation also provides a framework for understanding the small imperfections in the CMBR, the seeds of the universe's large-scale structure. These slight variations in temperature, amplified during inflation, correspond to tiny differences in density. As the universe expanded and cooled, gravity acted on these density fluctuations, pulling matter together to form stars, galaxies, and cosmic filaments. But where did these primordial fluctuations come from? To answer that, we must consider the strange and noisy nature of quantum fields. Even in a vacuum, emptied of all matter, cooled to absolute zero, and shielded from radiation, quantum fields persist. They fluctuate randomly, creating tiny variations in energy. These quantum fluctuations, magnified by inflation, became the first cosmic seeds, the precursors to the structures we see today. After inflation, the universe continued to expand and cool. Around 380,000 years after the Big Bang, it reached a critical threshold. Protons captured electrons, forming neutral hydrogen atoms. This decoupling of matter and light allowed photons to travel freely, creating the CMBR. But the story of structure building was far from over. As the universe cooled further, baryon acoustic oscillations, sound waves rippling through the primordial plasma, left an indelible imprint on the distribution of galaxies. These waves, driven by the interplay of gravity and photon pressure, froze into place when the universe became transparent, leaving characteristic patterns in the clustering of galaxies at a scale of 150 megaparsecs. Yet the true architect of the cosmic web was not ordinary matter but dark matter, an enigmatic substance that outweighs regular matter by a factor of 5. Dark matter interacts primarily through gravity, forming the invisible scaffolding upon which galaxies and clusters are built. While ordinary matter responded to photon pressure and formed BAOs, dark matter remained unaffected, anchoring the densest regions of the universe. The existence of dark matter was first hinted at in the 1930s by Fritz Zwicky, who noticed discrepancies in galaxy cluster masses. Decades later, Vera Rubin's observations of spiral galaxies confirmed its pervasive influence. Stars at the edges of galaxies moved faster than expected, revealing the presence of a massive, unseen halo of dark matter. Today, dark matter is central to our understanding of cosmic structure, yet its true nature remains elusive. The leading hypothesis posits the existence of WIMPs, but direct detection efforts have yet to yield conclusive results. Despite this, the gravitational effects of dark matter are undeniable. It shapes galaxies, drives gravitational lensing, and determines the universe's large-scale structure. Through the interplay of quantum fluctuations, inflation, dark matter, and baryonic processes, the universe grew from an almost featureless expanse into the intricate cosmic web we see today. From tiny seeds to galaxy-spanning filaments, each stage of the universe's evolution tells a story of balance between chaos and order. And yet, mysteries remain. What is dark matter? What sparked inflation? What lies beyond the observable universe? The quest to answer these questions continues, reminding us that while we have come far in mapping the cosmos, we are still at the dawn of understanding its deepest truths. The story of the universe, while awe-inspiring in its detail and depth, is far from complete. For all that we have uncovered, quantum fluctuations as cosmic seeds, the epoch of inflation, the scaffolding of dark matter, and the baryonic ripples that shaped galaxy clustering, there remain profound mysteries at the heart of cosmology. One of the most pressing questions is the nature of dark energy, the force driving the accelerated expansion of the universe. While dark matter serves as the invisible architect of the universe's structure, dark energy plays the role of a disruptive force, pulling galaxies apart and ensuring that the cosmic web thins over time. What is it? A property of space-time itself? A new quantum field? Or something entirely beyond our current understanding? This accelerated expansion also raises questions about the ultimate fate of the universe. If dark energy continues to dominate, will the cosmos end in a big freeze, with galaxies drifting so far apart that the night sky becomes dark and desolate? Alternatively, could dark energy reverse its behavior, leading to a big crunch, where the universe collapses back into a singularity? Some theories even suggest a cyclical universe, where each Big Bang is followed by a big crunch in an eternal cycle of creation and destruction. Another enigma is the asymmetry of matter and antimatter. The early universe likely produced equal amounts of both, yet today, matter overwhelmingly dominates. What mechanism caused this imbalance? Experiments like those conducted at CERN aim to uncover the fundamental processes that tip the cosmic scales, allowing galaxies, stars, and life itself to emerge. Moreover, while the observable universe has been mapped with increasing precision, it is but a fraction of the whole. The universe beyond our observable horizon is shrouded in mystery, possibly holding clues to the fundamental nature of reality. Are there infinite copies of our observable universe, as some interpretations of inflation suggest? Or does the cosmos end abruptly, beyond which lies an unknowable void? Then there is the tantalizing possibility of multiverses. If inflation can occur once, could it occur multiple times, spawning an ensemble of universes with different physical constants and laws? If so, how did our universe end up with the precise conditions necessary for stars, galaxies, and life to form? This question touches on the anthropic principle, a philosophical consideration that the universe's properties must allow for observers like us to exist. Even the structure we see today, magnificent as it is, may conceal deeper truths. The cosmic web, with its filaments and voids, reflects the interplay of forces in a universe of 4 dimensions. But what if there are higher dimensions influencing this structure? String theory and related frameworks suggest the existence of extra-spatial dimensions that could subtly shape the universe's evolution. Finally, there is the question of time itself. What came before the Big Bang? Did time have a beginning, or is it an emergent property of the universe's laws? These are questions that stretch the boundaries of both science and philosophy, demanding new ways of thinking and new tools for exploration. The story of the cosmos is one of ever-deepening wonder. Each discovery opens new doors, revealing mysteries that challenge our understanding and fuel our imagination. From the smallest quantum fluctuations to the grandest cosmic structures, the universe beckons us to explore further, to ask bigger questions, and to embrace the unknown. The seeds of structure may have been sown in the earliest moments of time, but the narrative they have grown into is far from over. As we gaze into the night sky, we are reminded that the cosmos is not just a collection of facts but a profound story, one we are only beginning to unravel. And perhaps, in the process, we will come to understand not just the universe, but also our place within its vast and intricate tapestry. Problems with Copernicus. Where are we going? It is a question that has intrigued humanity since the dawn of astronomy. The Earth spins on its axis while orbiting the Sun. The Sun, in turn, spirals around the Milky Way, and the galaxy itself moves through space, pulled by unseen forces. But when we zoom out to the grandest scales, the entire Laniakea supercluster, our galactic home, is moving, pulled toward a point in space hundreds of millions of light-years away. This destination, identified in the 1970s through the study of the cosmic microwave background radiation, was dubbed the Great Attractor. Our local group of galaxies, along with countless others, is rushing toward this enigmatic point at an astonishing speed of 1,000 kilometers per second. But what could be there? What gravitational leviathan lies hidden, pulling such vast cosmic structures toward it? The mystery deepened, and astronomers realized that the great attractor resides behind the zone of avoidance, the central region of our Milky Way obscured by dense clouds of interstellar dust. Observing this region required X-ray telescopes, which revealed the Norma cluster, a massive congregation of galaxies. Yet, even this cluster could not fully explain the immense gravitational flow. Further investigations showed that the great attractor itself is in motion, pulled toward an even greater structure. This new discovery, the Shapley supercluster, lies 650 million light-years away and contains the mass of nearly 10,000 Milky Ways. It is the largest concentration of mass known within a billion light-years of Earth. But the story didn't end there. In 2017, researchers proposed a counterbalance to Shapley, the dipole repeller, a vast underdense region nearly opposite the Shapley supercluster. While it doesn't literally repel matter, its gravitational weakness allows more massive structures, like Shapley, to dominate the cosmic flow. Together, Shapley and the dipole repeller create a colossal stellar river, a billion light-years wide, through which galaxies, including our own, are swept. Yet, this is only one of the peculiarities revealed by large-scale cosmic mapping. Another enigma challenges the very foundation of our understanding, the axis of evil. The CMBR, a relic of the universe's infancy, is extraordinarily uniform. Its temperature varies by just 1 part in 100,000, a testament to the homogeneity of the early cosmos. However, when scientists divided the CMBR into large segments, they found an inexplicable pattern. The temperature differences between quadrants align with the plane of our solar system. This alignment defies the Copernican principle, which asserts that no position in the universe is special. How could the vast, ancient cosmos possibly be linked to our local solar system? Some, like Charles Bennett of the WMAP telescope, suggest coincidence. Others, like Dominic Schwartz, acknowledge its stubborn persistence, even in data from the Planck telescope. This axis of evil remains a mystery, one that gnaws at the edges of modern cosmology. The CMBR is often called the baby picture of the universe, capturing the moment, 380,000 years after the Big Bang, when photons could finally travel freely. But what came before? How did inflation, a period of exponential expansion in the universe's first fractions of a second, begin? One idea suggests a sea of dense vacuum energy in the primordial universe. A quantum fluctuation could have sparked an inflationary bubble, growing rapidly into a universe. If this is true, there might be other inflationary bubbles, other universes. Perhaps they lie just beyond the CMBR, invisible yet potentially detectable through faint collisions with our own bubble. These collisions could leave imprints, subtle anomalies in the CMBR that scientists are actively searching for. The mere possibility of evidence for a multiverse electrifies the scientific imagination. If we could detect such an imprint, it would revolutionize our understanding of reality itself. Where are we in all of this? From the cosmic to the local, our address reads, Observable Universe, Laniakea Supercluster, Virgo Cluster, Local Group, Milky Way, Orion Arm, Solar System, Earth. Each scale reveals layers of structure and order, shaped by simple yet profound principles: gravity, dominated by dark matter, and expansion, now driven by dark energy. These forces transform chaos into beauty. Galaxies swirl in vast filaments, illuminated by the warm afterglow of the CMBR. The collective work of scientists like Copernicus, Shapley, Zwicky, Rubin, Zeldovich, Peebles, and countless others has brought us this far, revealing the intricate dance of matter and energy across the cosmos. Yet, for all that we know, mysteries remain. What drives dark energy? What is dark matter? And what secrets still lie hidden in the stars? The universe is vast, its story written in light and shadow, its answers scattered across time and space. And as we continue to unravel its mysteries, we are reminded of our place within this grand, unfolding narrative, both observers and participants in the endless exploration of the cosmos.